Hello, everyone, and welcome to IMI's Masonry Education webinar series. Ever wonder how to detail a stone cladding system? Well, I've been faced with that challenge before, and without the technical assistance of IMI and expert consultants like Picco Engineering to assist us, it can be a really daunting task to do that properly. My name is Mark Swanson, and I'm the director of the International Masonry Institute in the Minneapolis office. IMI is a nonprofit. We're funded by the Bricklayers and Allied Craft Workers Union. We have directors all around the country, and we're here to help you with your masonry questions. You can find us all on the IMI website, imiweb.org, in the About pull-down menu. For today's presentation, you will receive one learning unit / HSW credit. AIA reporting will be done, as well as certificates, and those will be issued within 2 weeks of today's presentation. We'd love to hear from you today. So if you have any questions during the presentation, please put those in the chat window, and if we have time at the end, we'll get to those questions. I'm really excited today to introduce our speaker this afternoon. He comes from a background of figuring out how things go together. And he's a licensed engineer in multiple jurisdictions. He's created his own consulting firm that works with designers, contractors, fabricators all across the United States and Canada. He has provided countless solutions to improving building performance and helping to demystify stone installations, making them easier to install. And that's why we brought him onto the webinar series today, to speak to you because of the results that he's provided in such a variety of stone installation scenarios. So let's get creative with masonry. Without further delay, please join me in welcoming Mike Picco.
Well, thank you for that introduction, Mark. I got a lot to live up to now.
You're welcome.
Thank you very much. And welcome everybody to the webinar. For those of you that don't know me, as Mark mentioned, I'm the founder of Picco Engineering. And after I graduated as a structural engineer, I started working with a precast company that also did a lot of stonework and marble work. And that's where I kind of got into understanding a little bit about stone and masonry, and really got attracted to it, was very interested in it. And from that job, I got hired by a stone contractor to kind of run their in-house engineering and run their facades and drafting department and engineering. And that's where I really got my experience, by being out on the field and really working with the installers and working with fabricators. We had our own fabrication shop that did a lot of the stone fabrication, and really cut my teeth and learned a lot from the masons on site. They really taught me a lot at the early parts of my career. And in 1992, our economy kind of turned. The company I worked with needed to downscale on the consulting part of their business. So I started up on my own in 1992 as a sole engineer and worked in the field of detailing and engineering for various stone applications, masonry applications, and have grown the company now to a staff of about 40 people. So we've been fortunate enough to work on many world-class projects over the years, and really exposed ourselves to various applications, a lot of unique challenges over the years, and really have grown to, I would classify as really experts in the field. So we touch a lot of parts of the masonry. We do design assist with architects to help guide them and set the path proper at the beginning. We work with fabricators. We work with, primarily most of our clients would be stone contractors or masonry contractors that would hire us to provide shop drawings, engineering, solutions, anything related to getting the job done, which could involve stone testing, various applications, mock-ups, and different things like that. So what I want to do today is take some of my experience, my experience over the years, and give you kind of 4 unique different applications. And you know what, I'm always looking for opportunities. Architects have so many choices out there now with materials and different things. So we want to get creative and find different ways to use our materials and really make it attractive to the architects. And when they do come up with unique systems, don't shy away from it. Find solutions, look for applications, look for ways and opportunities that we can make their visions come to reality. So I've got 4 different case studies here. One is a terracotta, a restaurant. Then I've got an exterior stone cladding project, Portland Courthouse. Vanderbilt University, which is more of a traditional type of masonry job, but we've done some unique things there. And then a very unique stone stair that we did in a high-end residence that I think is really interesting to share with you, just what's possible and what can we do out there. So we'll start with this first one here, is Gusto Restaurant in Toronto. And the architects wanted to do something really unique here with terracotta on the interior space of the architect. So they developed and designed this 3D wall of various ins and outs of terracotta and cutting them in different ways to create patterns. And they also wanted to integrate lighting into the walls. So leave some of the cavities open where they could shine light in and out. So, I mean, they approached us on it. We looked at it, gave it a lot of thought. You know, it was very challenging. We'd never done this before. So we actually got 4 or 5 pieces of tile and we brought them into our office and we studied them and looked at them and figured out how we could do it. We then worked with a mason that we know that likes these types of challenges and is willing to take on unique opportunities. And working with them, we tried to develop some solutions. So here's a model of the architect's one of the portions of the wall here, and you can kind of see how it steps in and out. And we cut sections through the various walls, and you can really see how much it goes in and out, and the cantilevers on some of these portions of walls. Some areas, the exterior of the tile was more than 2 feet off the backup wall. So we went anywhere from like 8 inches to over 2 feet out, and created a lot of kind of overturning and a lot of weight that we had to tie back to the structural wall, which was a little bit of a challenge. And how do we integrate this and tie it all in so we've got integrity to make it all act as a monolithic wall? So some of the concepts that we studied was using some solid block backup, filling some of the cores and tying it back to structure. So trying to create one line of block wall in the back or terracotta filled wall that we could act as the main tie back or the main structural wall, and then the cantilevers and the different portions would all be tied back to that. So concept was one thing. How were we going to do it? The mason was a little concerned as well. We all thought that building a small mock-up was probably the best to see if our thoughts and concepts were in fact going to work. So we started by building a small mock-up at the mason's shop. And what we used was, we used kind of a wire lath or an expanded mesh to bridge the tiles, and then conventional brick ties for the most part, tying back into a mortar bed, tied back to the structure, and then tying everything back to that wall. So we used masonry backup in some portions. Some of it was only the clay tile. So a combination of both. So a little bit of a challenging project. Here you can see how we use the block backup in the back, and you can see the extent of the cantilever coming out and how the lights fit in there, and was quite successful. We were really happy with the mock-up. Mason was quite happy with the way it was turning out, and most importantly, the architect was happy with the look as well. So from that point, we said, okay, now how do we get the information onto a drawing so we can clearly show the mason where the different details apply and how it applies, and into basically communicate all the field to the field, all the different conditions that we needed to apply. So we created an elevation, we did blow-ups, we created sections, And we worked very closely with the mason in developing some of these and what he thought would be feasible and what we thought we needed for engineering, and developed various conditions that he could then apply to various areas on the building. You can see how we've indicated some of the cores needed to be filled solid. We had a tie back to a lintel. Some of them were shelf angles, some was bearing on structure, some we built up with steel. So really a lot of unique different conditions that needed to be detailed and very clearly communicated on the drawings. Here you can see some other conditions, again, just various applications and different situations that we needed to clearly identify. Now, when we were doing this, we were getting some pretty high loads on the backup wall, which is stud. I mean, ideally, we would have loved to have a masonry backup wall to tie into, but it was an existing building. There was a stud wall backup that also needed to be used for the exterior of the building. So we actually took on the design of the stud wall backup as well, because we needed double studs in some areas. We needed heavier gauge studs where needed to pick up some of the loading, and minimize the amount of deflection on that wall as well. As I said, ideally a block backup wall would have been the best, but we had to deal with the situation, which very often we are working with metal stud backup walls, just because that's one of the main construction methods right now. You can also see that some of the portions of the wall were just a tile application, just a flat terracotta bonded directly to a cement board, and a typical thin set application. So here you can see we then got into the steel backup and all the steel detailing and all the metal studs. So that was given to the stud guy. Our masonry contractor did not handle this part of it, but we coordinated all that work to the requirements that were needed for our terracotta installation. And here you can see I've shown some of the pictures here of the finished. Well, this is during construction actually. And you can see how much these walls step out in some of the situations. We also have some soffit application up above. And again, just some other views that you can get an appreciation of how much this wall actually projects out in some of the areas. Here's a condition, some custom fabricated lintels needed to be fabricated to pick up some of the stone stepping in some of the locations. Again, just some other conditions of the walls and how they step out during construction. And here are finished photos of the actual interior of the restaurant with some of the lighting. And again, here you kind of get an appreciation. The unfortunate thing is that this project finished just before COVID hit us, and they've been mostly closed since they finished the project. So I hope that financially they can ride it out, but for places like this, I know a lot of the restaurants are really hurting, so we hope they can survive this, because it's really a unique installation that we were very proud to be part of. I also threw in here that concludes that project there. I also threw in this is another terracotta, glazed terracotta application, all on an aluminum grid system and mechanically clipped onto the wall. In this project here, we were actually we were responsible for designing the stud wall backup to receive all the terracotta application here. And the real challenge here was all the walls are square at the bottom, and they're all round radiused at the top at various radius conditions. So we had to actually twist the walls going up to create the geometry and not create any facet conditions. We actually had to design the stud wall backup and twist them as they go up the elevation. So it was a real challenge to design that. And you can see here some of the interior stud walls and the complexity involved there. We actually created a model of all the stud walls and gave an XYZ coordinate of every point of the stud at each floor level, and they were all surveyed, and datums were set on the floor, and measurements were provided. And here's how we established the connection. We designed a circular pattern on the stud wall that allowed the same connection to work with all different angles as the angles changed going up. And this metal connection was also allowed us to twist the studs as required to create the geometry. So, sorry, you can see on the right side there how the metal brackets were used to twist the studs at different angles and bear on the floors. And you can see how it created a very smooth transition on these walls of very complex geometry. So that, again, just another unique application that came out really looking fantastic. So let's change gears a little bit now. Now we're going to look at a Portland courthouse in Portland, and this is an aluminum grid system with a stone installation. And in this case here, we can see the building there. It's a 17-story building, and there's strips of glass and strips of stone. So there's it's kind of a hybrid curtain wall. So we thought the best way to handle this was to design the stone part of the structure similar to a curtain wall application. And the challenges here that we had were high seismic zone and the story drift that we had to deal with. We had to deal with a story drift of 3 inches. So again, being a very high profile project, a mock-up was extremely important, and the specifications also included a very regimented testing program that was checking water infiltration, air tightness, and obviously the structural performance during a seismic event. So I'll run through with you here the mock-up that we did and the development of the connections for the mock-up. So the mock-up consisted of a corner condition, a couple of pieces of curtain wall, and some stone, and the program needed to test for all the applications. Here you can see this is the stone layout. So the stone that was selected, the panels were rather large. Some of them were 6 foot by 4 foot approximately in size. So you can see there's kind of a mid-height connection of the stone. So the stone could not span the full height. We would have had to go with the stone would have been too thick and created too much weight, because with the seismic loading, the heavier you get, the higher the seismic loads came. So we wanted to keep the stone as thin as possible to minimize the seismic effects, and obviously respect the panel size that the architects wanted to use. So we went with top and bottom connections, but we also needed a mid-height connection to take the loading on the stone. So this was an elevation of the stone and the connection requirements for the stone. The next elevation you see here is the aluminum grid system. That's the verticals are the main structure, and the horizontals are the connections for the stone. So vertical grids were structural, tying back to the main structure. Horizontals were secondary members off the primary ones that were used to connect all the stone connections. And you can see here, our opportunity here was to basically take on the whole assembly. So the vertical members were structure. We integrated insulated panels in between them, air sealed them. So we had a weather-tight insulated assembly. And then outside of that is an air cavity and the horizontal connections to the stone. The other very unique one there on the top right is there's a slip connection. So the lower panel is fixed to the structure, and the upper panel comes in and slots into that we called it a chicken head connection there, that slots into that and allows for that horizontal displacement, but it's connected in and out. It's tied into the lower structure. So that's where we designed the slip connection to take the story drift. Unique conditions, little returns on windows. We connected the stones to the primary face stone and used small clips to connect back, so there was no additional requirements for connections on the small pieces. They basically were integrated onto the main primary stone. The other challenge was, how do we handle the corners? When the story drift is going to shift as much as 3 inches, how are we going to handle those corners without breaking? So what we designed on the corner was a hinge connection and a flexible connection to allow that corner to pivot and rotate as the floor shifted left or right or up or down in this condition. And it allowed that corner to rotate, pivot, without putting pressure on the adjacent panels. And we'll see when we did the mock-up, I'll show you some photos of the mock-up on how that actually worked. So here you can see a little better the way the primary vertical members are connected back to the structure, and how that gooseneck basically, or the chicken head, receives the panel above. So we're fixed at the top, and the panel's allowed to move at the bottom and shift. So that was the primary at each floor level. You had a vertical slip connection, vertical slip connection tied back to the main structure. So here you can see the mock-up going up. You can see the insulated panels at the lower level that are already installed. Clips are installed to hold them in place, and they're all sealed and caulked interior and exterior to give you an air seal. Here you can see the stone in place. This is after it's been wet. So here's the dynamic air test. So 15 minutes of water was dropped down at a rate of 5 gallons per hour, and an air jet was equating a pressure of 12 pounds per square foot onto the elevation and driving that rain onto it for 15 minutes. And then it was measured inside for any air leakage, any water leakage, and it performed well, no problems at all during that test. The big challenge and our big concern was, how was it going to perform when they shift that upper level over as much as 3 inches from the lower level, and you know, how our corner was going to perform. So the first test was to shift it by 3/4 of an inch, bring it back to 0, shift 3/4 of an inch in the opposite direction, back to 0, and run that for 3 cycles, and then observe for any observations, run the air and water pressure test again to see if there were any breaches during that type of movement. So this would be kind of a lower seismic event that we wanted it to perform and be able to perform with no remedial work required after a small seismic event. So that was that initial test, and performed well. The next challenge was moving it 3 inches left, bringing it back to 0, and 3 inches to the right, and measuring the performance. Now in this case here, we did expect some deformation, some breaches in the caulking and sealing, but the main goal was no panels breaking, no structural damage, no panels falling off. And you can see that, as you can see the shift there and how much it's moving to the right in this case. And here you can see how much the panel and the corner shifted out during the rotation and how it performed there. So again, we were very happy to see that it shifted, no failures in the panel, no cracks, nothing was observed as far as failing. And the way the mock-up was tested, it could move as much as 4.5 inches. So we decided, let's take it up to 4.5 and see what happens. And when we did take it up to the 4.5, there were some gasket failures, some weather seals, and some small cracks observed on some of the stones at the anchors. But again, nothing fell off and there were no real failures on it. So we were really happy with the way the design intent performed. And that was the way the project moved forward after the mock-up. So I do have a few photos here of during the construction. On the left, you can see the load-bearing connection there. Again, the geometry, although it looked very straight and simple, there were a lot of steps in and out to consider as we went up. The main structural engineer gave those cast ends there where we connected our vertical members to. There's adjustment in and out in the aluminum members, and once they were set in place, they were locked in. And once the lower panel was locked in, the top connection was installed and the next one inserted and fit in properly with the chicken head connection. Here you can see some of the panels in place. So basically, once those backup panels, which are our structural members, are in place, the insulated panels can go in. It can be weather tight. The glass can go in, and basically interior of the finishes can start going, because that is now weather tight. The horizontal members for the stone, and the stone can go in later while the interior starts the finishes on the interior. Here you can see that connection that we talked about, a little close-up of how that's working, and that flexibility of that movement joint there. That's where it occurs, and that's what we tested in the mock-up. Again, just a few more photos during construction here of how it was going up, and you can see that, you've already got lighting at the lower level, and you're still working on concrete work up above. So it went up, closing in the building, starting to work on interiors, and the stone could follow in later and not really impede anybody's schedule. Very often your stone is a critical path item, but in this case here, because we could seal the entire thing, it comes off the critical path and can follow up later. Here's just a few more shots that show the various stages of construction. Still pouring concrete at the top and completely sealed on the bottom. And here's a few photos of the end result of the building. Were some challenges during construction because of construction tolerances, and I always challenge the GCs and construction managers on why the mason or the stone mason has to work within 1/8 of an inch, and everyone else is allowed to pour their concrete anywhere within 1 or 2 inches of where they need to be, and we have to pick up all that variance later. So there were some challenges regarding site conditions there that we have to do some field adjustments and some special conditions to accommodate. But at the end, it worked out, and the building's pretty impressive. So let's change gears here a little bit now. Vanderbilt University, we're working on the Vanderbilt B right now, which is they're doing 3 new residential colleges there. And for the most part, it's a real traditional type of masonry installation here, a combination of stone, brick, masonry backup, a lot of solid filled, solid conditions. And you can see here we've detailed all the stone for the stone fabrication. All the anchors were detailed where special anchors were required. So it's a combination of conventional brick ties for a lot of it, special anchors for some conditions like the jambs, headers, archways. Here's a little bit of a blow up. All the stones were numbered, detailed individually. Shot fabrication sheets were done for each one. So we basically provided the full service on this, from design assist to the architects and helping guide them, and working with the mason, structural engineer on all the installation requirements. The nice thing about getting involved early on a project is we can influence a lot of the structure and a lot of the backup requirements or structural requirements really to suit the requirements for the installation of the stone later or the masonry. Very often we get stuck with structure that's been provided by a structural engineer on what they think may be required, but very often is not what we need or not the optimum solution of what could be provided. So getting involved early very often results in a much more efficient design and a much cleaner installation at the end. So I always encourage, if you can get involved early and have the influence of some of that, it's really advantageous on several fronts. So we often pitch to architects, bring us in early. We can give you a very small budget to at least give you some guidelines on critical areas, on what may be required structurally to receive the stone, and it makes things a lot easier later on. So here you can see how we've used some of the block backup to bear stone on. So we've built out some sections at various levels to create piers and different setbacks of the stone. Pretty conventional, nothing really fancy here, but again, having the influence to detail that and come up with the most efficient way for the mason and for the structure is very good. So one of the big challenges here, there were 7 large chimneys, and they were all up on a slate roof. So again, being involved very early on the job, a lot of the conversation was, well, when do these need to go in? How do we bring the materials up there? How are we going to integrate it in? When do they go? How do we flash it into the roof? How do we make sure we don't dirty any of the materials, and all the challenges of getting all these big heavy stones and big chimneys up on the interior spaces of these buildings. So our proposal to them was, why don't we build them on the ground and hoist them up in place, which is what we ended up doing. So rather than hoisting all the materials and masonry and mortar and building heavy scaffolding to receive all that material and build it in place, we said, let's build a platform on the ground. We'll build a steel structure heavy enough that we can hoist all this up in place. The structural engineer, we coordinated with them the requirements that we needed to sit these legs down on the structure within the roof, and made this installation super easy. Rather than hoisting all this material up on the roof, we built it all on the ground, no more than 15 feet up off the ground. The higher chimneys were split into 2 pieces, and we detailed them all as prefabricated chimneys. And here you can see some of the stone detailing required, some of the sections through it, how we, again, this looks like any conventional type of installation, but what we did is we integrated a steel structural backup, tying everything back to the steel structure. Now, it obviously had to be rigid enough that we had to hoist this all up in place without allowing any twisting or movement that would potentially cause cracking in the mortar. So it's a pretty robust steel structure. You can see where it's been split in 2 pieces because the crane had limitations because of the reach that we had to go. So we split it based on weight limitation on what we could handle with each part, and designed it as 2 pieces. Here are the 2 steel pieces that were built independently, married together in the shop, so we knew there was a perfect fit. And the other nice thing is, they were built on the ground, so they were dry set. First course was set with the lower floor, then it was brought down and built all independently. We knew we had a perfect fit. The connections were designed with sleeve connections, so once they were preset on the ground, fitted into place properly, dismantled and built, we knew we were going to have a perfect fit once they got up there. And then it was simply a bolted connection. The 2 sections were bolted together by going inside, so there was access allowed from the roof to get up inside to bolt them in place once they were done. So again, this is just being involved with the project early enough, having the influence of making these pretty challenging logistical chimneys very simple and very easy. And here's a short video of one of them going in place, and you can see, I'll run that here, of how that worked. And this is just one of them. And you can see how much easier this is than having to build that all in place way up there on the roof. And you can see there's one on the left there already in place. So I mean, from an installation perspective and having access up to that roof, you really don't need a lot. I mean, a couple of days of work. All the flashings are in place. You can see on the lower portion, the flashing's already all done. That's been done all on the ground. Very easy for the roof to tie the flashing in. And again, the pieces marry into each other, and you're basically done there. So again, looking for some of these opportunities. One thing, it's a lot safer building it on the ground, bringing it up in place. Logistically, way easier to handle. So a great opportunity, and we're implementing that. We're actually working on the next college, Residential College C right now, and we're doing the same thing on that one there because the success we saw on this project. Another opportunity is some of the fancy soffit pieces where they're integrating brick and stone. These were all done on a precast panel. So these were all built in the shop, integrated in, and then brought in in one piece. So again, opportunities to look for places where we can make the installation more efficient, easier, simpler, and a very good quality installation. Everything will get tuck pointed in those stones or caulked, depending on the specification. But again, looking for some opportunities. I also brought this example in. We worked at Yale University in the residential colleges, and some of the heavy archways going into courtyards had a lot of steel structure. So this archway was designed with steel columns, steel lintels across the top, and then U-shaped stones all hogged out to connect into the steel columns. And when I looked at it, I said, why don't we just pay a little more for the stone, which you're not really paying much more, because when you hog out a stone, they have to start with the full stone anyway and then pay to cut it out to have these steel columns in. Why don't we just design it as a structural stone archway? And we ended up eliminating all the steel, designing it as a structural arch, pick up all of our masonry up to the next level, and then we introduced the shelf angle above there for all the stone above. But again, having the influence early on, we were able to do that and say, get rid of all that steel. We don't need it. We're going to do this as a structural arch, and really was the benefit to everybody on the project because it really simplified things, made it a lot easier. And I would say the installation probably came out better by doing it this way than to try and tie all those pieces back to steel. So again, just a quick note of something else to look for when there's the opportunity. Here's some of the finished photos of the Vanderbilt, and you can see a lot of the complex stonework here and a lot of real heavy detailing. And you could see one of the chimneys there on the top, actually two of them. And again, here a few of the chimneys in the distance there that we hoisted up in place. Again, a really fantastic, really great looking masonry application. The next job I want to show you is something that was really unique to us. We called it the floating stair. And here you can see a detail of one of the stone treads here with 3 cables going through it. So I'll explain to you what we did here. The architect is a Toronto architect, Peter Clues. He does a lot of unique things. In this case here, there was a heritage home in a ravine. It was a lot of heritage requirements. It was a historic home, so there was a lot of limitations on what they could do with the main structure. But basically, they left the main structure in place and integrated, basically modernized all the inside. So they gutted the whole place, left all the stone on the exterior, built a new pool and a deck. But the main exterior of the home was kind of left intact as much as possible. And one of the challenges he had was he wanted to design a stair in an open space that was originally cantilevered off the walls. So the original concept was integrating the stair with cantilevered stairs coming off the wall. The unfortunate thing was that wall that they were cantilevering off was one of the historic walls, which was an old rubble masonry wall. And the structural engineers, when they looked at it, they said, there's no way you can cantilever that stair off there. You're going to have to build a structure to do that. So, which means furring out that wall, building a pretty heavy structure of columns and beams and very heavy stringer in order to cantilever that stair out. The builder that was building the home had done work with us before with stonework, so he reached out to us and kind of showed us his challenge and asked us for some ideas. And we said, why don't we just pull it off the wall and build it as a structural stone stair? We'll post tension it. We'll run some cables through it, and we will build it as a structural stair. The architect loved it. He loved the idea. The owners loved it. They said, you sure you can do that? And we said, yeah, we were confident we could do it. The other challenge we had, it's a pretty flat stair. You can see it's a long stair with a 3 to 5 rise to run ratio, which made it pretty long. So our bending stresses were pretty high on it. So the concept was to bear it on the ground at the bottom, post tension it, create it like a beam, create a beam out of the stone, and lean it up against the second floor, so that the foundation is really taking the load. The upper floor is taking the dead load, primarily the dead load of the stair because it's so heavy. It was over 10,000 pounds in total. So when a 200-pound person walks on a 10,000-pound stair, it's not going to have much of an effect on it once we're carrying that dead load. So we did a pretty extensive testing program on the stone to really understand the stone properties. We did threaded rod tests because the railing was going to be attached to the stone, so we wanted to understand the capacity of the stone with the epoxy threaded rods onto the edge. So we always test the failure. So we tested up the failure in tension and in shear, so we could really clearly understand the properties of the stone with respect to supporting the railing loads. Once we had all our stone properties, we did some preliminary analysis, and then we ran some stress tests. We worked in collaboration with a company called Webb Yates that has done some post-tensioning structures before with stone, and we've met them at some international trade shows and had some discussions with them, and we thought it was appropriate to bring them in and kind of oversee our analysis and guide us along here. So we reached out to them to make sure we were on the right foot, so they helped guide us along on some of this. Some of the challenges here was obviously the geometry and the way those stairs worked. When we're post-tensioning, we didn't want to have these stairs kind of shear into each other. So we had to create a key that allowed the loads to really distribute perpendicular to the forces of those rods that we were tensioning in the post-tension. So we really wanted to compress these stairs all together to really act like one beam. So the geometry of the stairs, you can see here's a section through it that shows all the railing posts going up, shows the pretty heavy foundation we had on the bottom to support the stair and the anchor points there. And there's a cut right through the middle that shows how the rods were fed through it and how we had a perpendicular plane to compress those treads all together. So those were hogged out right in the middle. So you didn't see that. As you can see, when we go back, it looks like it's just flat stairs going into each other, when in fact, the center portion of the stair is keyed into each other to create a perpendicular plane to marry force those stairs all together, and we had a very good bearing surface to load those steps into each other. There's a close-up there of how we had a very heavy steel bracket at the top, heavy steel bracket at the bottom, and then we post-tensioned those stairs, and I've got some photos that'll show it. You can see the railing details there and the way the threaded rods were used to support the glass railing off the edge of the stairs. Here you can see the complexity of each one of those treads and how it actually looks. So, you know, the perimeter looks like a very flat piece with a little reveal at the top, and then this key at the center portion of the stair, which is really invisible to the finish, but that's critical to the performance of this stair, was creating that key in order to load these stairs together. And then we also had grout keys pocketed into the stone so the grout could fit into each other. The other challenges are when we were setting all these stones in, we had to ensure we had full bearing. So we had a mortar joint there, but we also had to ensure that the mortar didn't fill in the holes, because the cables had to go up and they had to get grout filled after. So we put a little bead of silicone around each one of the holes in order to prevent the mortar from getting into and filling the holes, to ensure we had a clear flow to pressure grout the stairs at the end. Here's a couple of photos of the fabrication, and we dry set every piece, and we tested the holes to ensure that they were all in line with each other. We had a straight steel rod that went through to make sure that all the holes, the core holes, lined up in the fabrication shop. So everything was QC'd at the fab shop. Every single step was measured. Every hole was measured. We wanted to make sure that when it got on the job site that everything was going to fit properly. So the QC was really important. Then we provided a layout drawing for the stone installers. Again, very critical that everything was set in place to ensure that all the stresses and everything were working as we modeled it, because the pressure and the we didn't want to create any internal stresses if the bearing surfaces were not exactly perpendicular to each other. So here we can see a few of the photos of what's involved with doing this. So the first thing we did is we built a wood structure 3/4 of an inch below the bottom of the steps to allow to shim off that. So we designed that, braced it in order to carry all the stones. The stones were all dry set on that with the cores fed through, because really until they got pressure, they got post-tensioned and the holes got grouted and set up, they're basically individual stone pieces sitting on each other. So we needed that wood structure in place until the stone was installed, set, and became a structural element. You can see we had 3 pressure gauges at the top with the post-tensioning cylinders. So the bottom cables were just wedged in with a chuck. The top was pressured. We had pressure gauges measuring the pressure of each one of them equally, tensioning to the loads that we needed. You can see some installation, and here's the steel bracket at the bottom, designed to take the loads of the pressure from the cables and then anchored into the foundation at the bottom. Here you can see on the step there, the silicone bead around the holes to ensure that none of the mortar was getting in. And here you can see how the key, the way the cables are fed through, and then the way the stone gets married in, and here you can see it kind of getting down, put in place, and setting it in to final location with the straps. And that was done progressively with each step. What we wanted to do then, before we took out the shimming underneath, we wanted to do a load test. So the shims were all popped out, stone was in place, and then we did cycling loading. So we did cyclical loading where we installed some block, took it off, installed more block, took it off. So up till we had a full design load of basically 150 pounds on each step, I believe it was, at the final loading. I can't remember exactly, but full design load. And we had 3 pressure gauges, deflection gauges to measure any deflection when it was under full load. At the end of the full loading, with the full blocks on it, it deflected 1.5 millimeters. So it was about 1/16 of an inch total deflection under full loading. So we were pretty confident that once we had the 10,000 pound stone stair in place, and it could handle all these blocks with a 1/16 of an inch deflection, that if you had 4 or 5 people coming down that stair, it wasn't going to be a problem. So we were really confident. I'll give you a little. Next one here is we had a time-lapse camera set up on the job site just to monitor the construction. And what was really impressive for me was how fast they got these stairs installed. Now, we had built the structure, the temporary structure was built the week before. The installers went in the day prior and did all their layouts. You can see a chalk line snapped on the wall there. They had all their working points established and all their lines marked. But they started here. This was May 29th, first thing in the morning. And I'll see if I can stop that once it gets going. But so first day, they did all their layout. They got the cables in place. And that's the end of the first day. So they got the bottom anchored into the foundation. They got their first 2 steps in, and they're ready to go with the next one the next day. So that was day 1. Day 2, you can see that once they got set up, they flew along right up to 2 steps left at the end. So they got all these steps in on day 2, and day 3 was finishing off the top. So really, it took them 3 days, day of layout, and then 3 days to install the whole stair. Next step was to come in, get the thing grouted, and the cables stressed. So the floor was covered. This was after. Here was the load testing that we were doing after it was set up, and then that's protection at the end. So that was in July sometime. And here you can see some of the completed photos. So you can see that the stair is completely solid stone, no structure. We've done many stones over the stairs where, over the years where they build a steel structure or a concrete stair and then we clad it all in stone. So in this case here, there's no structure whatsoever other than the solid stone. The railings attached to the stone, and it is a pretty impressive look when you're looking at it. It's kind of eerie when you're standing underneath it, looking at just the stone there. But again, just another unique application of what we can do when we get creative with stone and masonry and all the different opportunities that we have. I went a little longer than I was hoping, but if there's any questions, that wraps up the conclusion. I kind of covered a lot. I spoke pretty quickly, but if there are any questions, I'd be happy to answer anything now.
Mike, thank you so much for all those, walking us through those fascinating examples of inspiring masonry. We do have a lot of questions. I can get to a few of them here. if I don't get to your question, feel free to reach out to Mike there at his contact information there on the screen, or also reach out to IMI. So here's, I think going back up to the initial project that you showed, the Gusto 501, I do want to highlight that that actually won the IMI JBC Innovation in Masonry Award last year. So we have that competition that's about to launch in 2021. So look for that. But that one was the winner of the JBC Innovation in Masonry Award last year, and we give out like $30,000 in prizes for that. So very cool that you covered that project. So on that one, on the terracotta, there's a couple of different questions regarding control joints in the terracotta and how you handle those, or if you even needed to.
We did have some control joints at floor levels or transition in structure. So we tried to create a lintel. We had some lintels where we had a soft joint, and we tried to mimic a mortar joint as much as possible. They sanded the caulk joint, so it looked like a mortar joint at the end. But we did have a few locations where we were concerned about some potential movement in structure. We didn't, I don't believe we had any horizontal ones other than in corners. All the corners were soft joints. So any transition or returns, we created soft joints there.
Okay. Also, here's a question. This is regarding the stone cladding curtain wall project, and this is regarding the chicken head detail. And the question is, did the chicken head detail terminate back away from the corner? There's actually two parts to this question, but that's the first part. Did the chicken head detail terminate back away from the corner? I'm trying to visualize that myself, but
yeah, it did. So there, each on each corner, you had the chicken head would stop or turn, because we designed that pivot connection on the outside with the hinge on it. So it was allowed to shift and move, and the outside was allowed to rotate around the corner.
Okay.
But there was a hinge. I mean, that hinge panel went back, I believe, 6 or 8 feet. So that whole corner was allowed to rotate and pivot as it shifted out.
Okay. Here's one on the Vanderbilt project. Any special soft joints that were used to accommodate the shrinkage of the concrete block as compared to the stone, which doesn't shrink, or the brick that expands?
Yeah, I mean, there's a lot of there are quite a few control joints there, strategically located. I mean, there's a lot of because of the heavy geometry and the ornate geometry, there's a lot of places you could hide control joints, usually inside corners of piers. So we try and section off, somewhere around 20 to 25 feet, let's say, plus or minus, wherever geometry allows. And sometimes we'll cheat that, we'll push it a little more just because we don't have an opportunity to create a joint. And then, architects are leery about having, a control joint that's very visible. So we try and conceal them as much as possible.
Right.
But yeah, there's a lot of discussion about control joints also goes in at the beginning of the project on where we can strategically put them in where they're least visible.
Right. Great. Here's one in regards to the prefabrication on that Vanderbilt chimneys. Do you feel that prefabrication masonry is being considered more often, and do you see any offsite masonry construction occurring, where maybe they're assembling it in a warehouse and then transporting to the site?
It's becoming more of a conversation item for sure, and it has been done in the past. There have been some applications where they have come out in large panels. We're working on one right now that has some pretty complex brick patterns and brick geometry that we are considering maybe prefabricating some of the masonry into a concrete backup and installing it like a lintel with the brick facing all on it. But yeah, prefabrication is becoming a lot more of a conversation, with modular construction being, a big thing now, that facades are being looked at in a similar fashion. How can we create modular kind of precast elements in masonry that can go in as large panels and built in a shop? So we haven't done a lot of them recently, but actually had a meeting with a precast fabricator just before Christmas, talking about exactly that. We're thinking about offering precast panels with brick facing on them, whether it's cut brick just on the face or whether it's full brick integrated in. So there's a lot of conversation around that, and I could see that becoming part of the construction in the near future.
Right. Absolutely. Great. Well, that's all the time we have today for questions. Thank you again, Mike. That was a wonderful presentation. Join us for our next presentation. You can check out our webinar offerings on the imiweb.org website. So until next time, see you, everyone.
Thank you very much. And if you have any questions, please feel free to send them through and I'll try and answer them. Sorry, I went a little over time. Didn't realize how long I went.
It's all good, Mike. Thank you.
Great. Thank you.